Welcome to CBS Easy.
Is the metals and nonmetals chapter feeling a bit overwhelming? Yeah, I get it. But don't you worry, you are in exactly the right place. We are going to cut through all the noise and focus on what you absolutely positively need to know to ace your board exams. So here's our game plan. We're going to start with the simple stuff, the basics, then jump into the really key chemical reactions. And we'll wrap it all up with a rapid-fire review of the questions that pop up on exams all the time. By the end of this, you're going to have this entire chapter on lock. Okay, first up, let's talk physical properties. You know, these are the things you can see, you can touch. They're basically the most immediate clues we have to tell if we're looking at a metal or a nonmetal. Right, so think about a brand new coin, or maybe a piece of silver that's just been polished. That shine, that unmistakable gleam, that's what we call metallic luster. It is the first and honestly the most obvious sign that you are dealing with a metal. We tend to think of metals as being super tough, right? I mean, that's why we build bridges and cars out of them. But, and this is a big but, in chemistry, there are always exceptions to the rule. And this one? Oh, this one is a classic exam question. You absolutely have to know this for your exams. Seriously, alkali metals, like sodium and potassium, are so incredibly soft, you can literally just cut them with a knife. Now, why is that? Well, it all comes down to their atomic structure. They only have one valence electron, which means their metallic bonds are much weaker. It's a classic one-mark question, so please remember this. You ever seen those super thin, edible silver foils they put on sweets? That right there, that's malleability in action. It's this amazing ability of a metal to be hammered and flattened into these crazy thin sheets without breaking. And when it comes to malleability, gold and silver are the undisputed champions. Okay, now let's talk about ductility, and get ready for this, because this is wild. Imagine taking a single gram of gold, that's tiny, and stretching it out into a wire that is 2 kilometers long. No joke. That's what ductility is, and it's exactly why we can have copper wires powering, well, pretty much everything in our world. All right, so now that we've got the basics down, let's move on to some other key properties. These ones require a little more experimentation, like how metals handle things like heat and electricity. So this is a classic experiment right out of your textbook, and it shows thermal conductivity perfectly. See how the lamp heats up one end of the metal rod? That heat travels all the way along it, melting the little bits of wax, and then pop, the pins drop one by one. It's such a simple but really powerful way to see it happen. Now for your exams, you absolutely have to know the best and worst performers here. Silver and copper, they're the superstars when it comes to conducting heat, but lead and mercury, they're pretty bad at it, so just lock those names in your memory. Okay, listen up, because examiners love to test you on the exceptions, and these two are the most common ones you'll see. Iodine, which is a nonmetal, actually has that metallic shine, that luster. And graphite, a form of carbon, is a fantastic conductor of electricity. Don't let these little trick questions catch you off guard. So, we're shifting gears now. We're moving away from physical properties and diving into the really exciting world of chemical reactions. Let's start with the most fundamental one of all. What happens when metals meet oxygen? So the general rule is actually pretty simple. Metal plus oxygen gives you a metal oxide. And these oxides, they're usually basic. That means if you dissolve them in water, they'll turn red litmus paper blue. A perfect example is that black layer of copper oxide you see when you heat up copper in the air. All right, now these are cool. Amphoteric oxides are kind of like the chameleons of the chemical world. They can act like a base when they're around an acid, but they can also act like an acid when they're with a base. The two key examples you need to know, and trust me, this is a guaranteed 3-mark question, are aluminum oxide and zinc oxide. Okay, I know. Equations can look a little intimidating, but don't be. Just take a second, pause if you need to, and write these down. If you can write out these two balanced equations for aluminum oxide reacting with both an acid and a base, you're setting yourself up for some easy marks. Okay, let's turn up the heat a little bit. Metaphorically, of course. Let's see how different metals react with water and acids. This is where we really start to see some huge, dramatic differences in how they behave. This table right here is pure gold. Seriously, it summarizes a huge chunk of the chapter all in one place. Just look at the pattern. The most reactive metals, like potassium and sodium, go absolutely nuts, even in cold water. But as you go down the list, the less reactive metals need hotter water or even steam, and then you get to the bottom with things like gold, and they just don't react at all. Okay, here is another one of those super important exceptions for your exams. Pay attention. While most dilute acids will give you hydrogen gas when they react with metals, nitric acid is the odd one out. It's such a powerful oxidizing agent that it immediately turns the hydrogen it creates into water. This is a very, very common question, so make sure you get it. So after seeing how all these different metals react with oxygen and water and acids, you might be wondering, is there some way to organize all this? Well, yes, there is, and it's called the reactivity series. This one simple experiment holds the key to understanding the whole thing. See, iron is more reactive than copper, so it can basically just walk in and kick copper out of its solution. But copper, it's not strong enough to do the same thing to iron. It's really just a chemical power struggle, and the more reactive metal is always going to win. And here it is, the reactivity series. Think of it like a league table for metals, ranking them from the most reactive at the top all the way down to the least reactive at the bottom. The rule is simple. Any metal can displace another metal that's below it on this list. Once you get that, you can predict the outcome of any displacement reaction they throw at you. All right, we're in the home stretch now. It's time for the final push. Let's do a super quick, rapid-fire review of the most common questions and definitions. These are the things you absolutely have to have locked and loaded for the exam. Okay, quick test. You ready? Why do we keep sodium in kerosene? Because it's so reactive with air and water. What are amphoteric oxides? They're the ones that react with both acids and bases. What's the non-metal that conducts electricity? Graphite. And aqua regia? That's the royal water, that special mix of acids that can even dissolve gold. If you know these, you are on your way to a great score. You see, this whole chapter isn't just about memorizing a bunch of random facts. It's about understanding the rules, the principles behind it all. That reactivity series, that's your secret weapon. It allows you to predict what's going to happen. You have the tools now to figure out any question that comes your way. Keep practicing with it, and you are going to do great. You've got this.
Thank you for watching with us. See you next time.